Welcome back to our next discussion in 7.4. We're going to continue on in talking about arc length and surface area. In the last discussion, we developed the formula for arc length, which I wrote down here. And now what we're going to do in this video is take this formula and put it into practice. Because of our limited knowledge of integration at this point, remember the only techniques we have at this point are we can evaluate the antiderivative directly, or by the power rule, or use substitution. We haven't learned other techniques of integration. We are kind of limited in the types of examples we can present, but there are a few that we can answer right now. And so let's go ahead and do that. And so the first example we're going to do is going to be one that we actually don't need calculus for, but it's just a way in which we can verify that this actually works. So we're going to measure the curve y equals 3x plus 5 on the interval 0 to 2. Why do I say that we don't necessarily need calculus? Because if you look at this curve, this is a straight line with a slope of 3 and a y-intercept of 5. And we're looking at two fixed points on this line. This is then the measurement of a straight line. We can use the distance formula to get an answer. But we're going to employ the use of calculus here and get an answer using our arc length formula. And so remember how the arc length formula works. It's a definite integral over this interval, as long as we make sure our function is continuous and differentiable in this interval, which it is. Then we'll take the square root of 1, that's just a constant that's fixed, plus we will need the derivative of this function squared. So I'm not going to be putting 3x plus 5 into this equation or into this formula. I will be taking its derivative. And so first, before we use the formula, let's figure out what dy dx is. What's the derivative of this function? And that is a constant 3. And we see why you don't really need calculus, and you're going to see the definite integral here actually breaks down and just becomes a constant. But let's go ahead and write this definite integral. We're going to be integrating from 0 to 2. That's the interval on which I'm given. The square root of 1 plus the derivative, which we saw was 3 squared, dx. And you see there's nothing in terms of x here. It is just a constant. We're going to get the definite integral from 0 to 2, the square root of 10 dx. This is just a constant, which can be pulled out. And we still need to take an antiderivative, the antiderivative of a constant 1 in this case, which is just x. Evaluate from 0 to 2. I plug in 2 to the antiderivative, I get 2. Plugging in 0 gives me nothing. And so we get an answer of 2 square roots of 10. Now, just to verify that this indeed agrees with our distance formula, we can actually go ahead and calculate this without using calculus. 1, 2, 3, 4, 5, y-intercept of 5, a slope of 3. And so at the point 0 or 5, and at the point 2 on the x-axis, we would be 6 plus 5, which is 11. Now I'll just simplify and go here. And so we have the length of this line. At 0, we're at the point 5, and at 2, we're at the point 11. And we really want the distance between these 2 points because it is a straight line. So let me just write down the points. We have 2, 11, and we have 0, 5. Distance formula. The length between these 2 points is the square root of the difference of the x-coordinate squared. So the x-coordinates went from 2 to 0, so that's 2 squared plus the difference between the y-coordinate squared, which is 11 and 5. That's a difference of 6. And so what do we get? We get the square root of 40. Now, at first you're like, wait, it's a different answer. It is not. Remember, we can simplify this root. Square root of 40 can be broken up as the square root of 4 times the square root of 10. You can write 40 as 4 times 10 and break the root up. And the reason I do that is because square root of 4 is 2. And we get, of course, the same answer. And so again, this initial example is just to verify that, yes, indeed, we are measuring the length of a curve, and it agrees with how we would measure the length of a straight line that we learned in algebra. Where it becomes, of course, more interesting is in situations where you cannot use algebra to get an answer, or geometry. Instead, you would need to use that formula. And so let's do a little more complicated of an example, where now we will measure the curve y equals 2x to the 3/2 plus 7 on the interval 0 to 2. We'll do 0 to 2 again, but a different curve. Now, first, this curve looks really complicated because of the fractional exponent, but what you're going to see is actually it makes it quite nice when we use this Arclength formula. And so remember, the Arclength formula is pretty much self-explanatory. We integrate over the interval we're given. 1 is just a fixed constant that we're going to need, and really what we need to be able to do is take the derivative of this function on this interval, which we can. And so using what I know from Calc 1, we would take the derivative of our function given, bring the 3/2 down, the 2 cancels, giving me 3x to the 1/2, subtract 1 from the exponent. And then the derivative of 7 is 0. So therefore, we have a derivative of 3x to the 1/2. And remember that when we plug it in, we are going to be squaring the derivative. Let me rewrite this real quick. 3 square roots of x. And so if I use my Arclength formula now, we would get the definite integral from 0 to 2, the square root of 1 plus my derivative, which is 3 square roots of x, squared dx. And although the derivative had a square root in it, it's great for the Arclength formula because now I'm squaring a square root, so it just becomes x, or positive on 0 to 2. And so we get the definite integral from 0 to 2, square root of 1 plus, now of course don't forget the 3 needs to be squared as well, 1 plus 9x dx. We need to square the entire derivative. Now we can evaluate this definite integral. Now at this point, we do need to remember something we learned from Calculus 1, and that is U substitution. We have a composition here, right? We have a function inside of a root, a function inside of another function, and we are going to substitute in to evaluate this definite integral. I will let U be 1 plus 9x, because if I just have the square root of U, I can evaluate that using the power rule. That's a great substitution as long as you have the derivative multiplied into this integral, which we do because the derivative is just a constant, 9 dx. And remember from Calc 1, if all you differ is by a constant, a multiple constant, then we can fix that by using a property of integrals that says constants can be moved in and out. And so I'll put a 9 on the inside and a 1/9 on the outside. What this does for me is really nothing. Right? This is 9 over 9, which is 1. So I haven't changed the value of this definite integral. What I've done, though, is I've put the 9 inside that I need to do the substitution. I've taken the over 9 and pulled it out. That's a property of definite integrals. Constants can be moved. And now we can do our substitution. I get a 1/9 on the outside from the constant adjustment that needs to be made. Inside the integral, we will get the square root of u. The root doesn't go away, but now underneath it is just u. The 9 dx becomes my new differential du. And then remember that this is a definite integral, so we also need to change our bounds. These bounds are for the x variable. I need bounds for the u variable. And so how do we find these bounds? Remember, if I let x be 0, we have a way to find u. Right? X used to be 0. If I replace x with 0, we see that u is 1. So this implies u is 1. That's my new lower bound. My old x bound was 2. What does that imply about my new u bound? When x is 2, 9 times 2 is 18, plus 1 is 19. And so my new upper bound for u is 19. So I just make a change all the way around. Therefore, I can ignore everything before this point and evaluate this definite integral. And so now I will use my power rule that I know from calculus to get an antiderivative. So that's 2/3 u to the 3/2, evaluated from 1 to 19. So I take my antiderivative, I plug in my bounds. Let's go ahead and pull the 2/3 out, so that's 2 over 27. And then plugging in 19 here, we have 19 to the 3/2 minus 1 to the 3/2. Now 1 to any power is 1, so I'm just going to write 1 here. Even though it's 1 to the 3/2, I simplify that. 19 to the 3/2 doesn't simplify nicely, so I will just leave it as this. And although this doesn't look like a nice answer, we can put it in a calculator, get a decimal if we wanted to, but this is the exact form. This is the value of the arc length of this curve on the interval 0 to 2. Now, because of what we are limited knowledge in calculus, because of this formula, it's a little bit complicated, right? It involves a root, the square of a derivative underneath. And unless we can evaluate this directly, like it ends up being a constant, or use a U substitution, something like this, we're a little bit stuck, right? Either we need this to be a constant underneath the root or a linear expression underneath the root if we want to be able to evaluate this. And so for that reason, we're kind of limited to these types of examples at this point. When we learn in the later chapter about our techniques of integration, we can come back and answer this question with a little bit more involved types of curves. But for right now, this is the kind of extent that we can evaluate it. And what we're going to do in the next video is we're going to come back and explore a kind of following step to Arclength, which is going to be now surface area. Because just like at the beginning of chapter 7, where we took regions and found areas, and then we revolved those regions and found volumes, in the same way, we measured an arc length. Now we will revolve that arc and create a surface, and therefore we want to measure surface area. So in the next video, we'll come back in the last part of 7.4, which is going to be evaluating a surface area problem, taking a curve and revolving it about some sort of axis. All right, so I'll be talking to you guys soon.